This is CSAT Sample Test 4, Question 16. This question reads, let Si be a sequence of integers obeying S, Si plus 5 equals I minus 1, for I is 0, 1, 2, and so on, and S0 is 0. We're asked to give a non-recursive expression for, in part A, one such sequence Si, and in part B, all possible such sequences Si. We're told that different expressions for different subsets of I, such as odd or even, are allowed. Where should we start with this? What we expect to do in this question is to investigate a few examples, begin to spot a pattern, and then eventually be able to write down the general form of that pattern and prove it. So, given what we have in the question, where makes the most sense to start? We're given S0 is 0, so let's plug that into this equation. S of S0 plus 5 is 0, given that I is 0, minus 1. Since S0 is 0, this tells us S5 is minus 1. Now what can we do? We have another value of a number in the sequence, so we can put it in again. S5 plus 5 is 5 minus 1. Since S5 is minus 1, this tells us S4 is 4. Next we put in S4, and in this way we generate S9 is 3. In fact, all we're doing is taking the index of S, subtracting 1 and moving it to the right hand side, adding 5 to the right hand side here and moving it into the index. And so our next one gives us 9 minus 1 is 8 on our right hand side, and 3 plus 5 is 8 on our left hand side. So S8 is 8. We can continue doing this, giving S13 is 7, since 8 plus 5 is 13, and 8 minus 1 is 7. The next iteration would give us S12 is 12. Can you begin to spot a pattern yet? In fact, we notice that for our multiples of 4 that we've seen, S something equals the same something. This seems like an important pattern. So let's investigate it a bit further. We might want to claim that this is true, that is, for I is a multiple of 4, Si equals I, and then we could try and prove it by induction. Let's think a little more about why it's true. Between each multiple of 4, there are 2 steps, and we interchange the left and right hand sides twice, adding 5, subtracting 1. To try and see what happens in general, let's take the case that SA equals B. If we apply our rule, then SB plus 5 is A minus 1. Now, the key step is that we apply it twice, so let's apply it again, and this gives us A minus 1 plus 5 is A plus 4, and B plus 5 minus 1 is B plus 4. And so SA plus 4 is B plus 4. Not only does this tell us why S4 is 4 and S8 is 8, and so on for all the multiples of 4, this can also tell us about numbers that aren't multiples of 4. For example, if we went from S5 to S9, we know we're adding 4, and in fact we can see that as we go from minus 1 to 3 to 7. And so, how can we work out our entire sequence from this? Given S0 and S5, we can work out all of these numbers, and so on. But is every number part of this list? In fact, what this expression tells us is that if we know S0, S1, S2, and S3, then we can add 4 as many times as we like to generate anything in the sequence. So we only need to know what these 4 numbers are. We already know S0. Can we work out any of the others? Notice that by our rule, S5 should be 4 greater, taking it in reverse, than S1. If we put this into action, we see that S1 is minus 5. So we know what S0 and S1 are. Do we have any way of working out S2 or S3? In fact, each of the numbers we've seen here, on the left-hand side, the index, is either a multiple of 4 greater than 0, or a multiple of 4 greater than 1. S2 and S3 don't correspond to these, and so it feels like S2 and S3 are somehow separate. We have our 2 patterns here, and S2 and S3 don't fit into this. This might give us some freedom to choose what they are. Remember that we expect to find this, because we're told to find one such sequence in part A, but all possible sequences in part B. Perhaps S2 and S3 are related in the same way S0 and S1 are. We know these are fixed, so we can ignore them for now, and think more about S2 and S3. As we've remarked, these seem separate, unrelated to the other constants. And so, let's try some things and see what works. This is normally a good approach to something like this, like we did with the first part, and we'll try and spot a pattern. And so, let's just guess something that could be S2. For example, 7. Now what? Remember, we can apply our rule. Adding 5, subtracting 1, we get that S12 is 1. What's wrong with this? We get a contradiction, since we know from our initial conditions that S12 is 12. So this can't be right. What's wrong with picking S2 equals 7? Notice that we've already seen a 7 in our sequence, and so when we move 7 to our left-hand side, we get S12 again. But it's already defined. What does it feel like's going on here? It seems like we're not allowed to repeat the number 7. Why might this be? Are you sure that it's true? We think that SA is not equal to SB for A not equal to B. That's what we remarked from this statement. How could we prove something like this? We essentially do it by contradiction. Let's say they are equal. Then, what can we say about them? Using our rule, then, this must be true. How can we rewrite these? Using our rule, it's just A minus 1 and B minus 1. But, clearly adding 1 to both sides gives us that A equals B, a contradiction, since we know they're not equal. And so, we've proved that each number in the sequence has to be distinct. More importantly, what does this tell us about S2 and S3? Remember that all the numbers we had here were of the same form. We're adding 4 each time. We have numbers that are multiples of 4, and we have numbers that are 3 more than a multiple of 4. And so, we know that S2 and S3 can't lie in these categories. Why is this helpful to us? If S2 and S3 don't lie in those two categories, they must be of the form 4k plus 1, or 4k plus 2. Let's try one of these. Let's pick the first one. Let's say S2 is 4k plus 1. This is a completely arbitrary choice. So, if S2 is 4k plus 1, what can we say? We can apply our rule. This is the only thing we can do in this question, pretty much. So, it seems like the most likely thing we need to do. Applying our rule, we get that S4k plus 6 is equal to 1. What can you see about the number 4k plus 6 that's helpful to us? It's actually a multiple of 4 greater than 2. And remember, we know about this. So we can rewrite it as 4 lots of k plus 1 plus 2. The reason we wanted to do this is because of the fact we deduced last time about adding 4 or subtracting 4 from both the index and the right-hand side. And so we can subtract as many 4s as we like. For example, k plus 1 4s, giving us that S2 is 1 minus 4 lots of k plus 1, or 1 minus 4k minus 4. But remember that we know what S2 is in terms of k already. Now we can solve this equation to find the value of k which works. But in fact, the equation will be 8k plus 4 equals 0, giving k is minus a half. Is this a valid solution? Remember that k is an integer. Through this whole question we're dealing with whole numbers. And so this in fact gives us a contradiction. And so S2 can't be of this form, and hence must be of the second form. Now we can try the same thing again. Applying the rule gives us S4k plus 7 is 1. And, performing this step again, subtracting multiples of 4 from both sides, we get that S3 is 1 minus 4 lots of k plus 1. This is useful because we now have a relationship between S2 and S3, like we said before that we expected to get. And so now, for a particular value of k, we can find the whole sequence. And so, let's try and answer part A. Find any such sequence. Let's pick a value of k. The most simple to use will be 0, so let's start with that. What does this make S2 and S3? We just substitute into our two expressions to get that S2 is 2 and S3 is minus 3. Now, let's remember the results we saw before for the other half of the sequence. Remember that we've worked out that the numbers do different things based on whether they're a multiple of 4, 1 more, 2 more, or 3 more. We're allowed to think about these different sets, as remarked in the hint at the end of the question. And so, what if I is a multiple of 4? Then we know Si is exactly I. What about if it's 1 more than a multiple of 4? We know that S5 is minus 1, or that S1 is minus 5, and we know for each 4 we increase the index by, we increase the right-hand side also by 4. So in fact, it's proportional to I. plus or minus some constant. In this case, our constant would be minus 6, giving us I minus 6, since this works for S5. For every 4 we add to the index, we add 4 to the right-hand side. We can do the same thing with the cases 2 and 3. S2 is 2, and so S6 is 6, and so on. Si is I, for all I equals 4n plus 2. And similarly, this one is a constant, is I, plus or minus a constant, and in this case, when I is 3, Si is minus 3, and so we have I minus 6. And hence, we've defined one sequence, which works. Next, we need to do it in the general case for part B. We've already done most of the working, so we just need to adapt what we've done so far to the general case. Remember that in our general case, we use expressions in terms of k for S2 and S3. Now, we only need to make a few small changes. Everything in the S2 sequence is shifted upwards by 4k. Everything in the S3 sequence is shifted downwards by 4k, or by minus 4k. And so, we can really easily write our general solution from here, by adding 4k to our 2 terms and subtracting 4k from our 3 terms. And remarking that this is true for any integer k. Because remember, our initial conditions only determined 0 and 1. We got to choose what 2 was, and 2 determined 3. Hence, this is true for any integer k. And so, we found this general solution, making this the end of the question.